Swayam Prabha. Digital India. Educated India.
So our topic of discussion right now is dynamic recrystallization, and in the previous lecture we started discussing about the mechanisms of CDRX.
Okay, so let's take a quick recap of the previous class before we proceed today. So we have been talking about this process, this phenomenon called dynamic recrystallization, and we have seen that there are different forms of this particular phenomenon, and these are DDRX, CDRX, and GDRX. Okay, discontinuous dynamic recrystallization, continuous dynamic recrystallization, and geometric dynamic recrystallization. So far we have covered these two, DDRX and CDRX, and we have also talked about the mechanisms through which the nucleus forms in these two cases. DDRX occurs by the same mechanism as in static recrystallization, that is through nucleation and growth, and the dominant mechanism for the formation of the nucleus is the grain boundary bulging mechanism. So we have talked about that in detail. And then we started talking about the CDRX process, and it is quite different from the DDRX in the sense that in this particular phenomenon, there is no well-defined nucleation and growth stage. Rather, it occurs uniformly across the lattice through a process which involves progressive transformation of the dislocation subgrain boundaries into high angle boundaries. And in that process, more and more dislocations accumulate, and eventually there is a lattice rotation also, which turns these low angle boundaries into high angle grain boundaries, and that is how the new recrystallized grains are formed. Okay. And with regard to that, we have already talked about the mechanism as to how exactly that happens in case of CDRX, as to how the low angle boundaries form and how do they turn into high angle boundaries. We have discussed that in the previous class. Okay. So now, going forward on this particular topic, CDRX, we will also see some other mechanism by which this can happen. Okay. So this one that we are going to discuss happens by progressive lattice rotation near grain boundaries. In the previous case, also there was some involvement of the lattice rotation, but there was another mechanism which was operating, that was through the dislocation accumulation along the subgrain boundaries. So here there is a lattice rotation near the grain boundaries through which the misorientation can also increase. So as we have seen before, dislocations arrange in low angle boundary configuration. In short, we can call them as LABs. And this occurs near the original grain boundaries by cross-sleeve. So the arrangement of the dislocations in this kind of low angle boundary configuration is known as dynamic recovery. We have seen before that the recovery occurs during the static recrystallization process also. Recovery is the stage which precedes the recrystallization. So here also the recovery can take place, and this occurs primarily by the rearrangement of the dislocations, right? And for this to happen, we have seen that, for this particular phenomenon, stacking fault energy plays a major role, right? Because for the dislocations to be arranged in such manner, they will have to cross slip. And for cross slip, you need a high stacking fault energy, right? So this is something we have discussed before also. So dynamic recovery is a process through which the dislocations arrange themselves into low angle subgrain boundary kind of configurations, and stacking fault energy plays an important role in this particular process. So now coming back to this mechanism, once the dislocations rearrange into low angle boundary configurations, the grain boundary migration also occurs. And as the migration is stopped at the triple points or the triple junctions of the grain boundaries, stress concentrations will develop at such sites when the migration is stopped. And as a result of that, grain boundary serrations develop, driven by the stored energy difference across the boundaries. Now, this migration can also level out the small serrations and therefore the grain boundary bulge will first double up along the non-sliding boundaries. And this would occur at large strain. While the dislocations arrange and form the low angle boundaries at lower strain. Okay. So once the bulges form, sliding can still occur in small areas of the grain boundary, and the rest of the boundary has to accommodate the strain by plastic deformation, leading to formation of a mental kind of shape. So the process can be depicted with this diagram. So you have boundary sliding at in the beginning, as I said before, and this sliding can be stopped at these triple points at the grain boundary triple junctions, and therefore stress concentrations will develop around this. So this leads to the serrations in the boundary and then ultimately as the sliding still continues after the bulge forms, it will turn into a mantle kind of shape. A mantle, you can say that it is a truncated kind of shape or a trapezoidal kind of shape like this. Rather, you can say a truncated cone or a trapezoidal kind of shape, as you could see from here. So these grain boundary bulges that you have now within the mantle or even outside will be subjected to non-uniform shear. And as a result will rotate, leading to asymmetric shape and ultimately the formation of the subgrains. right? So the next stage is the lattice rotation along the grain boundaries, as I said in the beginning itself. All right, so with this rotation, ultimately the subgrains form, and those will act as the nuclei for the strain tree grains. So both of these mechanisms that we talked about for the CDRX involve lattice rotation, but depending on the strain which is applied on the material, there could be other mechanisms also through which CDRX can occur. For example, during the deformation, micro shear bands can form, and the CDRX can also occur through the formation of such MSBs. Okay, so let us talk about this particular mechanism now as to how exactly the MSBs lead to the occurrence of CDRX. So first, as we have seen before, the dislocation substructures will form through the DRB process. So now these dislocation boundaries that you have, for them to be turning into high angle grain boundaries, the misorientation across them has to be increased, right? This is something that we have discussed before also. So as the MSBs form in the next stage, the misorientation increases. The misorientation across the sub-boundaries increases. And further deformation leads to formation of more MSBs, which in turn leads to a network of MSBs in the grain interior. And the average misorientation also increases. Right, so the process can be depicted by this particular diagram over here. As the material is deformed more, MSBs will form inside the grains, and in fact it will lead to a network of MSBs as the deformation is increased. Right, so it has created domains inside the grain. So let us say if you talk about any two adjacent domains such as A and B, these microsphere bands are now separating these domains. So now if you just magnify this and look at these two domains, as the deformation is increased, the misorientation across the domains will increase. Okay, so this boundary that you see over here between A and B, that is the subgrain boundary formed by the dislocations, and as you continue the deformation, the misorientation across this boundary will increase. Okay, and when the misorientation across these boundaries is large enough, then high angle boundaries will develop. And new equiaxed grains will form. So these are the grains which are now strain free, and in terms of morphology they are equiaxed, which means they are rounded kind of grains in terms of the shape. And this process actually happens heterogeneously. These equiaxed grains will first form at the intersection of the microsphere bands. What you can see by these pink color grains that you have over here, those are the equiaxed grains which form in the beginning as the misorientation becomes large enough. So first it starts at the intersection points of the microsphere bands, and then gradually it spreads across the band as the misorientation increases further, and as a result of that, this equiaxed microstructure propagates over the entire lattice. So that is how here the recrystallized grains will form and consume the rest of the material. So when these boundaries turn into high angle boundaries and these equiaxed grains spread across the entire lattice, then it will lead to the recrystallized microstructure. Right, so the boundaries are actually colored here. These pink color boundaries that you see, these are actually the boundaries which are already turned into high angle boundaries. While the blue ones are still low angle and they are in the process of evolving into high angle grain boundaries. And dynamic recovery again plays an important role here by assisting the dislocation rearrangements for forming such subgrain boundaries, and also helping into shaping the strain-induced grain boundaries into proper grain boundaries. Okay. So this is how the entire microstructure will be recrystallized through the formation and propagation of this kind of equiaxed grains with the help of these micro shear bands which form as a result of deformation. Okay. But for such network of MSPs to form, you need a large strain, a large amount of deformation, and therefore this kind of mechanism will be more prevalent when a very large deformation is being applied. That means, you'll have to go for this kind of processes known as severe plastic deformation process, in which the material is deformed to a very large strain, and therefore you can expect this kind of micro shear bands to form in large numbers so that a network of these MSBs can be created for them to serve as the nucleation sites for the new equiaxed grains to form. All right, so these are some of the mechanisms of CDRX for forming the new recrystallized grains. Right, so few important things to remember with regard to the DDRX and the CDRX process, and how you differentiate them, that would depend on such parameters. One, of course, is the stacking fault energy, as we talked about, because for the DDRX process to occur, you need the dislocations to accumulate rather than movement of dislocations, or having the cross slip of dislocations. You need the dislocations to build up, right? So that you can develop that strain energy gradient across the boundaries for the nucleus to form, right? So that's the driving force over there, the strain energy gradient or the dislocation density gradient, right? And for that to occur, the dislocations have to accumulate, right? So there you need to have lower extent of cross slip so that the dislocation build-up can occur. On the other hand, the CDRX occurs through the progressive increase in the misorientation of the subgrain boundaries formed by dislocation rearrangement, and this increase in the misorientation can only occur when more and more dislocations accumulate along these subgrains, and therefore you need a cross slip of dislocations to occur, and therefore CDRX will be more prevalent in high stacking fault energy material. Okay, and which mechanism will be prevalent in a particular material, that of course depends on the material property, right, as we talked about, but it might also depend on the deformation conditions in terms of the temperature, strain, and strain rate, right? For example, here the mechanism that just now we talked about, the MSP mechanism, this may be prevalent at very large strain, like what you have in case of severe plastic deformation, right? So these are the few things to remember when you talk about dynamic recrystallization and the different forms of dynamic recrystallization.
All right, with that we can wind up this lecture. Thank you for your attention.